So in homework 3, you're asked, among other things, to do a power analysis for a t-test. So just in case we went over that a little too quickly in lecture, I wanted to give you another video that goes into a more detailed explanation for how to do such a power analysis. So first, let's get a little bit of background out of the way. So just as a reminder, we're thinking of we have some variable, some that we're measuring. So this could be, for example, the average queue length at the end of a simulation of an airport security line, for example. And so it might be that I run the simulation and the average queue length after running it for a week-long simulation ends up being 10.5. And then I run the simulation again with another set of random numbers and it's 9. And I run it again and it's 8.6. And I do that over and over again and I get all of these different average queue lengths. Now, I have been told that if this simulation is good, that it will then reconstruct queues that have an average queue length of a particular value. So we can say that we hypothesize that these average queue lengths come from some distribution with some mean, and let's say that mean is, I don't know, 7. And so if my simulation is running properly, then it will have a distribution of average queue lengths that is agreeable with a distribution that has mean 7. Now there is an implicit assumption here that this distribution is normal. So it's a normally distributed average queue length. So it's these numbers up here are assumed to be normally distributed. And so really this hypothesis is not on the distribution, but it's on the mean. So given that I know the numbers are normally distributed, then is the mean of those numbers equal to 7? So when we have made the restriction that we know that our distribution is normal and our hypothesis is on the parameters of that distribution, then we are doing a parametric statistical test. So the t-test is a parametric statistical test because it requires us to make the assumption that the data are normally distributed. And then we end up doing the test on the mean. So what we end up doing is we calculate a sample mean. So from those particular numbers, we can go down here and say, all right, the sample mean is, and I could calculate whatever the arithmetic mean is of those particular numbers. And the arithmetic mean then, so if I were to take another set of numbers, so if I run to another set of experiments, so I went down here and I ran this experiment again, and I might get, whatever, these other numbers. Then I could then from them calculate another sample mean, and this sample mean is probably going to be close to this sample mean. But they're not exactly going to match up. So basically, I am going to have some distribution of means, of mean estimates, I guess I should say. So this first one, this kind of blue colored one, this Y bar might show up here. And this green one, might have shown up here. But there will then be a whole bunch of others that if I were to drew on more and more and more of these samples, then they might show up in different spots on this number line and so on. And I end up getting then a distribution of sample means. And so in other words, I could take like a histogram of all of these data, and that histogram would end up looking pretty bell-shaped. And that histogram would have some then mean value, which hopefully would be right on the population mean. So, and then it would also have some standard error. And so that standard error of the mean estimate is what we refer to as the standard error of the mean, or the SEM. So when you hear people saying error bars or standard error bars, they're usually referring to the standard error of the mean estimator and not the standard deviation itself. This y response variable up here might have its own standard deviation, but the standard error of the mean down here is going to be totally different. And so generally the standard error of the mean for an arithmetic mean estimator is going to be the standard deviation of the population divided by square root of n, where n is your number of samples. And so it is always going to end up being smaller than the standard error of the distribution. And so as I take more and more samples, the standard deviation itself doesn't change, but I get more and more confidence that my standard error is hopefully going to converge to the actual mean of the distribution. It's hopefully going to collapse around the actual mean of the distribution. But my question for my small sampling statistics is, when you give me just a few samples like this, so whatever this y value is, so another data set down here. And so my question is, did these data come from a distribution that has the mean that I'm looking for? And so what the t statistic does is it says, all right, let's take the mean estimate you've got, that's the one sample, and let's subtract off your hypothetical mean, and then divide that by the standard error of the mean, or at least your estimate of it. And so our estimate of the standard error of the mean is, it's also right, estimate of square root or standard error of the mean. So that's the estimate of the standard error of the mean. And so S here is our sample standard deviation. So that is our estimate of sigma. And this here is our hypothetical mean. And then there is our sample mean. Now, what we've ended up doing here is we've just basically rescaled that distribution up here. So this is a distro of estimates, of y-bar estimates, and we've just rescaled it. We've standardized it. And so the t-statistic is sort of just a standardized version of the estimates of the mean. So if I were to go up here and then plot the different t-statistic values that might come out of here for different data sets, then for, let's say, this blue y that I started with, it might have come up with a t-value of here. So maybe this is the t-value for that blue one. And then for this green one, then it might have had a t-value that's over here. And then there might have been a bunch of other t-values in between for all sorts of other data sets. And if our hypothesis is correct, if these did come from a normal distribution with a mean of 7, then this standardized version, the t-statistic, should be centered around 0. So there should be sort of a 0 that's in between here. And this t-statistic will have a shape, which is, let me see if I can draw this a little more cleanly. It'll be symmetric, and it'll look sort of like a normal distribution. But it turns out that it is a little different than normal distribution. It becomes more and more like a normal distribution as the number of samples go up, but at least for low numbers of samples, it's not quite shaped exactly like a normal distribution, but it's the same idea of roughly a bell curve. And so so this down here represents if the hypothesis is correct. And in other words, that's if the expectation of y is truly equal to mu, then we would expect our t values to all come into this distribution. So what we can say is, well, so what you're telling me is if I calculated a t-statistic that was way out here, then that is extremely unlikely, and I probably could reject my hypothesis. So if my y bar generated this t-statistic, then I can pretty much say that the expectation of y is not going to be equal to mu. So my hypothesis is not correct. So I would have, this is a reject. So what that tells me is that I can set a threshold above which, and this is for a one-sided t-test, just for simplicity, that if I set a threshold, let's say here, let's try to, again, I'm going to try to draw that a little more straight here. So if I were to set a threshold, let's say here, then this threshold is saying that everything on this side of the threshold, everything on this side of the threshold is a positive result, meaning that we have detected, so I'll say it's a positive detection of a difference from the hypothetical, from a hypothesis of a mean of 7 or a mean of whatever the mean is. And anything on this side is a negative result. And so when I set this, then I notice that some of the true values down here are going to be above that threshold. Even when they're way out here, there's still some, although you can't see them because they're so tiny, but there's still some possibility that I could get under the null hypothesis t-values that happen out there, but it's pretty unlikely. So we set this threshold recognizing that we are going to have some false positives and true negatives. So the false positive rate, which is kind of colored in red here, false positive rate, is otherwise known as type 1 error, and we often use the Greek letter alpha to represent that. So then the other side of this, underneath the curve here, I guess I could maybe use the highlighter. So this area underneath the curve that's to the left of that threshold, those are good negatives. So we have our false positive rate, and then we also have our true negative rate. And you can just view that as 1 minus alpha. All right, so I've talked about false positives and true negatives. So when I talk about statistical power, I'm really interested in the other half of it. And so the real question is, then how do I figure out my false negative rate and my true positive rate? And so with that, I have to kind of know what a non-hypothesis looks like. So in other words, I'm going to, just to clean this up, I'm going to erase. Oh, that was a little more than I needed. Erase this line that I drew earlier. And I'm saying, well, how many different ways could my hypothesis be wrong? And if you think about it, because this is a parametric test, so I'll go and highlight that again. So this is a parametric test. Then we know that that even if our hypothesis is wrong, we are still restricting our data to come from a normal distribution. And so everything's still going to be the right shape, but it might just be shifted over. So when we calculate t-statistics, And in fact, we're also implicitly assuming that it's not only the same shape, but we're assuming that any alternative hypothesis has the same variance as our hypothetical distribution. So it's not only normal, but it's normal with the same variance. So I guess I could write that in here. So it's normal and same variance. So we are taking that for granted in this parametric test. So it really is only a test on whether the means are different. So based on that, if I were to calculate test statistics for an alternative hypothesis, then what I'm basically saying is that it's going to look just like that shape over there, but it's going to be shifted over. And so maybe I now draw an alternative one, which I will try my best to draw to be very similar in shape to the one I already drew, and I know I will probably fail miserably. But imagine that this blue curve that I just draw is like a copy of the black curve that I just shifted over to the right. And because the means are different, then it's sort of like the centers are incorrect. And so there is some distance between these two, which we'll talk about here a little bit later, but that basically represents this distance between these two hypotheses. And so from here, everything above that threshold, so if I were to go and highlight, everything above that threshold, that purple threshold that I drew, are positives. And so we've got this region that I guess maybe I'll color in orange here that are under the blue curve in this, and it's actually kind of under this red curve as well, but so that's everything underneath that curve that's on the right of that purple, and that is going to be, those are our positives, but those are our true positives. And then we've got some of these that snuck in. So if I were to, maybe I won't highlight those, maybe I'll just squiggle over those. So these ones here that I'll squiggle over in blue that are on the left side of that curve, well, those are our false negatives. So they came up negative, but they should have been positive. So the little blue section there, that's represents our false negatives. So the probability of that, or the false negative rate, otherwise known as type 2 error, which you might be familiar with as beta. And so then we now, the true positives here, so the true positive rate, that is otherwise, you could view that as 1 minus beta, and that's also called statistical power. So when we talk about having statistical power, then we talk about being able to have a very good true positive rate. So basically what this means is when your p-value is greater than alpha, then you can conclude that you can so-called, accept the null hypothesis. So that's one way to view statistical power. In other words, what we're saying is that you have very little risk of accepting a bad hypothesis, because if you have high statistical power, then you would have detected it. So high statistical power means that I have high detection ability, and so with high statistical power, if I do not make a detection, then and only then can I conclude that my hypothesis might actually be true. Otherwise, if I have low statistical power, then I might not have detected a difference from my hypothesis, but that still doesn't mean that I actually can have confidence that my hypothesis is true. It just means that I couldn't detect it, that these two curves were too overlapping. All right, so the only thing I want to add to this sort of general background here in how we define all of these things goes back to this line that separates these peaks. So maybe I'll highlight that in green. And so that line right there, um, that represents kind of the distance in t space here. So if I were to sort of imagine, how far away are those two peaks? Well, I've got, y bar minus my hypothetical distribution over s divided by square root of n. And then I also, so that sort of is what generated, this distribution over here. And then I could say, well, what if I would have picked the right mean? So what is the actual mean for my data that would have put me in the right location? And so if I were to sort of subtract then y bar minus the actual mean, so this was, I guess, the hypothetical mean over here, and this is the actual mean. They have the same standard deviation, so everything else would be the same. And so the length of this line is basically going to be the distance between the actual mean and the hypothetical mean, all scaled by this standard error of the mean down here. So that's kind of the distance of that line that I highlighted in green. And this is also where statistical power comes into play, because what this is going to tell us is that if we have a lot of samples, then we can sort of guarantee that even small distances, so I'll go back, we can sort of say how big, I guess that's another way to view it. How big does this numerator between the actual mean and our data mean, how big does that have to be to generate a distance that is very large in this t space? And what this scaling by the standard error of the mean does is it basically tells us that as we get more and more and more samples, then we are able to detect a smaller and smaller difference between means. In other words, a smaller and smaller difference between means will generate a large distance in t space. So as you make this square root of n larger and larger and larger, then you're making the standard error of the mean smaller and smaller and smaller. And by dividing a small number by a smaller number, then it ends up making the distance in t space even larger. And so this is the mechanism that allows for more and more samples, giving you more and more discrimination ability. With more samples, you end up effectively spreading these distributions apart. And as you spread these distributions apart, the orange area is going to get larger and larger and larger, and thus the statistical power is going to get larger and larger and larger. So with more samples, you get more statistical power. With more statistical power, you get less type 2 error. And with less type 2 error, you're going to have less false negatives. And that's going to mean that you're going to be able to actually trust your negative results. You're going to actually be able to trust these high p-values only if you have large sample size. So then the real question is, how large do I need my samples to be for me to be able to trust these things? And that's what we do the power analysis for. So what I'm going to do is pause here and we will then move on, but just to give you a break in the video, we'll stop here, and then if for those of you who didn't want the background, you could just start with video 2.